Okay, cool. So welcome to the fourth meeting of Berkeley. And today we're going to be going over this pretty cool concept called reverse engineering. Does anyone have an idea on what reverse engineering is?
Yeah. 185.
Did I say 180?
You said 180. I was waiting right there.
Oh, my bad. Yeah. All right. But yeah, that's exactly right. You're essentially, given a program and then you're supposed to like take it apart and kind of like look into how it's like implemented and how it's done. So we're going to go a little bit into it, just, the very basics. And if you guys haven't taken 61C, this may be a little bit challenging. I'll do my best to try to, push you into solving your first challenge, but by all means, this is not a comprehensive review of, the topics covered. So just a fair warning. And please be sure to ask a lot of questions because this is, I'm probably going to butcher the concepts and stuff, but yeah. Okay, so if you want to start solving the challenges towards the end of the presentation or during the week, I'm going to post the challenges up on the Discord. You should download Docker if you have like a Linux machine or Ubuntu, or if you have SSH connection to an EEX instructional account, you can do that as well. But if you want to play the challenges on your own machine, please download Docker. Okay, cool. So reverse engineering, like you said, you're basically given a finished product and you're trying to take it apart, understand how it's designed, and look at basically the behavior of the program. And it's the reverse of forward engineering on what you guys have been doing in 61B, 61A, and your other design classes. And it has some pretty interesting applications. So, reverse engineering, it creates a lot of pretty cool products. So for example, if you wanted to recreate a product that is closed source, for example, the Game Boy machine or the YouTube API, then you'd have to reverse engineer it and re-implement it on your own and then kind of do your own thing with it. So if you've ever played with a GBA emulator on your iPhone, GBA for iOS, that's a product of reverse engineering. If you've ever used like a YouTube to MP3 converter, that's also a product of reverse engineering. Also, if you want to understand what the program's doing, if you want to extend features like game cheats, like aimbots, wall hacks, and stuff like that, jailbreaking iPhone, you need reverse engineering to do that. And last but not least, to find underlying security vulnerabilities in closed source programs like iOS, IoT devices, and stuff like that, you'll need reverse engineering. Any questions on what it is so far? Okay, so we're just gonna like dive into like, the things you need to know to reverse engineer a basic C program. And to kind of understand how we're going to reverse engineer things, we kind of have to take a step back and see what computer programs are and how they're being run. So you all are familiar with a programming language, Java, C. And here we have like a C program, C++, and we write like hello world, right? And how that's being run on the CPU or how your computer understands it is it needs to be compiled down to this thing called machine language. Think of it as a bunch of ones and zeros, but it can also be represented in some human readable form that we'll get into later. So when you're kind of, programming something, you're doing whatever you want with int main or whatever, right, in your favorite programming languages. And then you have a compiler specific to your CPU, which compiles it down to this machine language that the CPU understands. And then your CPU continues to run it. And more often than not, if the source code isn't available to you, you're going to be getting the machine language representation of the program. And this is where we have to start reverse engineering things. Okay, and taking another step back, what are computer programs? Computer programs, think of it as a bunch of instructions and a bunch of data, right? You have like a huge blob of bits and bytes, and those are all instructions that tells the CPU what to do and how to manipulate data in the program. So for example, we have something over here, like we have a variable, we set it to 1337, and then we're performing an operation on it, right? We're adding it, we're performing a conditional on it, and then we're calling certain functions and stuff like that. So think of computer programs as a bunch of instructions, right? And you're manipulating data found inside the computer program through those instructions. Okay, and you might be wondering what those instructions look like. And when I'm saying instructions, I'm more alluding towards the ones and zeros that are being run by the computer in the CPU. And what do those instructions look like? For Intel CPUs, they look like this. You know, there are a lot of different languages, I would say, or instruction sets for machine languages, and Intel x86 is one of them. If you've taken 61C, RISC-V was used as the instruction set architecture, but we'll be using Intel as it's more popular, and RISC-V isn't there yet. But yeah, so for Intel instructions, we have like operations that we can do on certain variables, right? So every CPU, think of it at, every CPU has like 8 registers, okay? And think of registers as variables, right? And they're specific to a CPU. So you might be wondering, like, what is this EAX, EVX, ESP, EVX? Just think of it as variables that the CPU has, and you're performing operations on those registers. So for example, the very top one, we have move EAX 0. That just means that you're moving 0 to the register EAX. Simple enough. Move EVP to EVX. That just means you're moving the contents of EVP into EVX. Any questions so far? Yes.
What kinds of things can a register hold? Can it just hold a number, or can it hold like a string or an object?
Yeah, so generally, registers only hold 32 bits of data, right? So we're kind of limited on what we can hold in a register. But yeah, they hold like integers, and they hold addresses to other places in the computer. So when we're referring to an object, we probably have an address associated with it, and then we can perform manipulations on that address. Which brings me to this next directive, dword pointer. So basically what that does is it moves whatever's in EBX into the address stored inside ESP. So again, like the concept of addresses might be a little bit abstract to all of you, but just know that computer programs, when you're like looking into memory or reading or writing to memory, there's like an address associated with each area of memory. And then you can, write to it, read from it. And dword pointer is a way of getting the contents of that address out and where you can read and write. Any questions? Okay. And there are other operations you can do. Yes.
What's dword?
That's a good question. I think it's data word. Double word? Is it double word? Okay, double word. I'm not really sure what that represents, but I'm pretty sure like words are like sizes specific to a specific instruction set architecture, right? So in the case of Intel x86, a word would be 32 bits. 16? Okay, yeah. 16 bits, and then double word 32. Yeah, makes sense.
Yeah, it is double word. It's just the size.
Ah, okay. There we go. My bad. Any questions? Okay, cool. And you can perform other operations on these registers as well. You have add, subtract, multiply, But the general rule of thumb for Intel x86, Intel syntax, is that you have the operation, and then you have the destination and the source, right? So the source is 0 in this case, and you're storing that into EDX, right? That's source and destination. That goes the same for add, right? Add is the destination is ECX, the source is EDI, and you're basically doing ECX equals EDI plus ECX. No confusion here? All right, cool. Okay, now this is another beast. Do you guys all know what the stack is? The data structure. Yeah, we covered that in 61A or B. But essentially you're pushing and popping. It's a first in, last out order. Yes. You're like pushing data onto the stack, and then you're popping data from the top of the stack. And that's essentially what you do with the stack, right? And that is a, yes.
I think that's a huge.
Yes. Yes. I got I got the wrong picture. I made these slides like an hour before, but yes, you're right. That's a queue. This is a stack. So essentially, a stack is super important in computer systems, and all you need to know about it, if you're not familiar, is that it's used to store local variables. It's also used for, calling functions, passing arguments and stuff like that. But for the challenges for today, all it does is just stores local variables. And what I mean by local variables is, say you're in a function frame, and you declare an X, an A, and B, right? It pushes these local variables. It creates like space on the stack so that you can reference these local variables, right? So we have very limited amount of registers. We only have 8 in Intel x86. And sometimes it'd just be better to just store things in memory. No confusion here? Okay. And essentially, we have this register dedicated for the stack called ESP, which is the stack pointer. And that always points to the top of the stack, right? So whenever you want to access something in the stack, if you want to access the very top element, you just call dword pointer on ESP, or you call push. If you want to access the second element, you do ESP +4. Does anyone know why it's +4? Not +1? Yeah. Every register can only hold 4 bytes. And yeah, that's at least for Intel x86. Right, and if you wanted to access the third element in the stack, you do 8 plus ESP. Okay, and as for stack operations in x86, if you do push ECX, what that does is it decrements ESP by 4 bytes, and then it stores ECX into the top of the stack. And the same goes for pop. So if you call pop EDI, what that does is it looks at ESP, the top of the stack, it pops that out, so it increments ESP, and then it takes the topmost element from the stack and then stores it into whatever register that you specify here. Is there any confusion? Okay, cool. So here's your first challenge. Why don't you guys work together and determine what ECX is at the very end of this instruction right here. Some tips I'll give to you. It's probably helpful to draw a stack diagram. Remember that registers are 4 bytes big, and the operations syntax is usually operation, destination, source. What does the first 2 lines do? Any ideas?
Values in the register.
Right. So EAX is now equal to 1337. EDI is now equal to 400. Anyone want to tell me what the stack looks like after push EAX?
Make one value for
1337? Yeah. And what happens to ESP?
it gets bumped up.
Okay, I didn't really visualize that well in my diagram, but yeah, ESP gets decremented by 4, and in that decremented space, 1337 gets allocated into the stack. It gets copied onto the stack. And push EDI is the same. Subtract ESP by 4, and then you push EDI onto the stack, which is 400. Cool. And then EVX is equal to 2, right? Because we're moving 2 into EVX. What does the next instruction do? What does the D word pointer directive do? Yes.
So, get the values for.
Yeah. Right. Yeah. So keep in mind that ESP is an address, right? So ESP is like basically a pointer to the top of the stack. So if we're doing ESP plus 4, that's going to point to 1337. And if we call dword pointer on it, dword pointer is going to look into that address, copy the values stored at that address, and then store it into EAX. That's essentially what it does. So yeah, you're right. EAX is now equal to 1337. What happens when we pop? Yes.
So did EAX change at all over the course of time?
Did-
Does the pop clear the value of EAX?
We didn't pop any.
Sorry.
The push.
It seems like EAX was 1237 and now it's still 1237. I just want to make sure I'm understanding.
Yes, you're correct. Yeah, EAX stayed the same value the entire time. But how we got this new 1337 was different in that we looked into the stack, we pulled the value from it, and then we set it to EAX.
Essentially, you just like, you can think of it like storing it on stack. Stack is essentially like permanent storage. Well, if you mess around with EAX, then like, say you change EAX, but you want it to be 1337 exactly again, then you just look on stack. Oh, wait, it was 1337 before. You can just pop that onto it, and then boom, EAX is back to its original thing because we stored it using push.
Yeah. All right. So what happens when we pop? Okay, so when we pop, remember the push and pop operations on the stack. When we pop, we look at the top of the stack and we decrement it by 4, and we take the value on the top of the stack and store it into ECX in this case, right? Okay. All right, and then again, add ECX at EAX. That's basically doing ECX equals ECX plus EAX. Okay, and the final pop, we get EVX is 1337 because that's the top of the stack, right? And then we decrement ESP by 4. Now it's at the very top. EVX now holds 1337, and we see that ECX holds 1737. And then when we do this addition, we get the final value 3074. Any questions? All right, so those are kind of like the basic operations that they do in assembly. And there's like another set, and there's like tons of instructions, like don't get me wrong, but these are kind of like the majority makeup of instructions that you'll see when you're reverse engineering programs. So these deal with like control flow and comparisons, right? So if you do, for example, on the very top, CMP, that stands for compare. And that basically sets this other place, like this register in the CPU to 1 if the destination is equal to source, right? And then if you want to do like an if statement, right? You want to jump to different places in memory. Yeah, you want to do like a conditional branch. You want to check if you compared, you want to check the results of what you compared before. So then, you can do like jump not equal. So if the 0 flag is 0, then we jump to another memory address. If the 0 flag is 1, then we jump to an address. And remember that compare sets the 0 flag depending on the values of destination and source. The very last instruction, jump, is an unconditional jump. It just jumps to a specific place in memory without checking the 0 flag. All right. What does this do?
So it starts off with EX as 37 and
Yeah, that's essentially it. Does anyone see why? Like in the first iteration, we start off with 1337, and then we subtract by 1 right here in line 0x1. And then we compare, is EAX equal to 0, right? And then the next line says, if it's not equal to 0, then we jump back to address OX1 right here. And you keep doing this, keep doing that until it hits 0, and then you return. Okay, cool. All right, so now you might be wondering, how do I view all this crazy stuff? How do I view all these instructions and all this assembly and stuff like that? And there are a lot of tools to do it. And one of them that I wanted you guys to try out was Binary Ninja. It's an in-browser tool, at least the cloud version is, and it's free. So go to that link. You have to register for an account. But if you are familiar with other tools such as GDB, you can use that as well to disassemble programs and to debug it and stuff like that. There's also Ghidra or IDA Pro if you have a lot of money. Yeah, so did everyone get this URL? We're good? Okay. Okay, so I have a set of challenges that you guys can try out. If you go to this link right here, that will take you to a Git repository, and that holds a whole bunch of challenges, a bunch of binaries that you guys can try out and try to reverse engineer with Binary Ninja. I'm going to start with the first challenge, and you guys can see like how it works and everything. But do we have any questions so far? Yeah.
I looked at it and there's a couple bugs in there, so I submitted a PI.
Oh, you did?
That should hopefully work.
Okay, all right, thank you, I appreciate it. Anything else? Good. Yeah, so hit up that GitHub address. Let me check out that PR. But what was the issue?
The Git complement seems to be like for only your account. Although I'm not sure about that. And then the GCC command, you wrote stack protection instead of, you wrote no stack protection instead of.
Okay, don't pull from this GitHub repository, but download Docker and register for an account at Binary Ninja. I appreciate it. Yeah, so work together, download this GitHub repository. There are instructions on the README on how to run these programs using your Docker image and how to use Binary Ninja. And slides are on the website. I'll drop the link in the on the Discord. Hello, sir. What?
You shoot me an invite to the Discord.
Oh, did I not invite you to the Discord? Oh, man. What?
This is really cool.
Is it?
Yeah, you did a good job.
Oh, thank you.
It's like way more preparation than I ever did.
Are you serious? I did this starting in the afternoon and I was like freaking out. Because I was like, do I go into the like these certain concepts or do I not?
You
And I had
actually made this in just a single afternoon. Dude, that's impressive as shit. Dude, just like message us and we'll help.
What?
Yeah.
What is that?
Just message us and we'll help.
Oh yeah. Yeah, you're right.
Exactly, yeah.
Next time.
I was bored out of my mind on my 161 project. So
Oh, you're doing 161 right now.
yeah, I'm doing 161 right now. It's the project 2. Do you remember that?
I've never took 161.
Oh, you never took
Never
161.
took
Oh. Oh, it's essentially creating a database from scratch, like client and like full client and everything. It's essentially like a Google Drive kind of thing, basically. And you're supposed to like allow different users to access it and all that. It's crazy.
So
Yeah, and you have to make everything.
when you guys download the
visually-
GitHub repository,
That's the hardest part, yeah. It's
you'll
real
see
fun.
chow 1, 2, and 3. Don't look into source. Those are the answers. So chow 1, 2, and 3. What you would do with those is in Binary Ninja, you would go here, new session once you've already logged. Oh, yeah. Choose a file, and then you can start disassembling. So in my case, I'll do chow 1.
Guess what did it do?
Do chow 2, and then I'm going to continue. And if you try to run these programs, you most probably won't be able to run them unless you're on a Linux machine. It's probably best to use the Docker image that I wrote out in the README and run it that way. But to decompile it, you can just use Binary Ninja on your host machine and take a look. Okay, and you might have something like this. A lot of this may seem very confusing, but just kind of a good rule of thumb for doing these type of simple challenges, you want to start off at main, right? So like in Java, you have public static void main, you go to the main method. And this is written in C, so in this case, we have the main function right here on the left side. So these are all the functions found by Binary Ninja in this little challenge, right? So you go to main 1. And then you have this kind of code graph, right? And if you like zoom in, you'll see like a bunch of the instructions that we talked about. Maybe some that we didn't cover, but you still should be able to solve this challenge. Does anyone know why this splits? Oh, right here. Yeah, so the reason why they kind of have this in like a graph and not like a huge dump of like an instruction file is that, you know, it makes it easy to see like where control flow goes, right? So if there's like an if statement, you know, If it's jump not equals, then it goes here to access denied. And if there is a jump, or if there's no jump, then you go to access granted. So it just kind of shows you where the different paths are in a program. And you can kind of infer where you want to go given the strings that Binary Ninja gives you. Yes,
What does JNE stand for?
jump not equal.
How can I find out more about instructions that I don't have?
Right. So you can Google it. It's so for example, so usually if you find like an instruction that you don't really understand, as you can see, I visited this before. Yeah, so if you see like an instruction you don't understand, you just search up this Intel x86. Make sure you put in Intel x86 because there are other instruction sets out there that may have similar, readings and stuff. So, yeah. Another very important tip we'll give all of you is that do not try to understand every single line in this program. Part of reverse engineering is knowing where the important parts are. So if we scroll up here, you'll see like a bunch of weird stuff, right? Like all this get PC thunk. You're doing a bunch of stuff with the stack. There could be some argument passing and stuff. We don't really want to focus too much on it, especially if you just started learning about this stuff today. But you kind of want to know, given the clues in this program, in this control flow graph, where you kind of want to look and kind of backtrack your way to try to find the right answer. That's your dinner?
What?
That's your dinner?
Oh, no. I was coming from downtown, so I was at my friend's house. And I decided I'd get dinner afterwards. But, yeah, awesome.